Hello viewers, today we will discuss about different types of sets. Number 1, finite and infinite set. A set is said to be finite if it consists of specific number of different elements, that is, if in counting the different members of the set, we already discussed members, elements and objects are same things. Okay, so if in counting the different numbers of the set, the counting process comes to end, otherwise the set is called said to be infinite set. That is, when you count the numbers of elements in the set, if it is countable, we can say it's a finite set, otherwise it is called infinite set. For example, the set of vowels of English alphabet, that is A, E, I, O, U. So the vowels are A, E, I, O, U. So it's a finite set, it's a countable set. Only 5 elements are there. Now the set of n of natural numbers. What is natural numbers? Starts from 1. So you will write 1, 2, 3, 4 up to infinite. That's why it is called an infinite set, because here the counting will not stop at any time. So it's a infinite set. Example of infinite set. Finite set and infinite set. Now null set or empty set or void set. A set having no element is called a null set. We denote a null set by the Greek letter phi. What is phi? Phi means a null set. In a null set, there is no element present in it. For example, set A, x is such that x is a natural number less than 1. Now, natural number starts from 1. So, you cannot say a natural number less than 1. That's why it is a null set. There can't be any element in this set. Second example B, the set of girl students in a boys school. So you are given it's a boys school. In a boys school there is no girl student present. That's why it will be a null set. We denote a null set by a phi, not phi, it's phi. Okay, phi denotes the null set. Next is singleton set. A set consisting of one element is called singleton set. Example A, x is such that x is an even prime number. Now we know that prime numbers have only one divisor. So only there is one even prime number is there, which is 2, because 2 is equal to 2 into 1. That's why it is 2. Now this set consists of only one element, that's why it is singleton set. Next is the set of lady prime ministers of India. In India there is only one lady prime minister, she is Indira Gandhi. So your set will consist of Indira Gandhi. Indira Gandhi. Okay, this is your singleton set. This chapter is very theoretical, so you have to write the definition of each terms, so that if it comes in exam, you can write in the exam. Okay. Now it's number 4, subset of a set. If every element of a set capital A is also an element of another set capital B, then A is called a subset of B. That is, each and every element of set A is also present in set B, then A is called subset of B. But A and B may have same number of elements. That's why we write A is subset of B. Here A and B can be equal. A or B can be equal. That is, A is a subset of B implies x, for all x belongs to A, it also belongs to B. Here X represents any element of set A, that is belongs to set A, then it implies X belongs to set B also. A set A is said to be proper subset of another set B if every element of A is also an element of B, but B has at least one additional element which does not belong to set A. Now set B has at least one element that is not present in set A, that is set B has more number of elements than set A. Every element of set A are also present in set B, but there exists at least one element in B which is not part of set A. Then we can say set A is a proper subset of set B which does not belong to set A. Then we write A is a proper subset of set B. This implies A is a subset of B but A not equal to B. In this case, capital A and capital B has different number of elements. Set A has less number of elements than set B. Every element of set B are also present in set B. For example, if I draw, this is your set B, this is your set A. This is called Venn diagram. In Venn diagram, we denote every set by circles and the elements by dots. These elements are present in set A. Now set B is this and set A is this. Now set A is a proper subset of set B because set B consists of more number of elements than set A, but every element of set A are also part of set B. That's why set A is called a proper subset of set B. In this case, A is not equal to B, but for this case A can be equal to B. A and B may have equal number of elements. Now you have to learn these things too. Remarks number 1, phi is taken as subset of any set A. For any set capital A, phi is said to be its subset, that is phi is a proper subset of capital A. Why so? Because if you take no element from set A, it is called phi. Now phi is subset of any set and A is a subset of itself. We can write A is a subset of A. Now A and A are equal, so you can write A is a subset of itself. Okay, this is subset of a set. This is very important for this chapter. Next is number 5, equality of sets. Two sets capital A and capital B are said to be equal if A is a subset of B and B is a subset of A, and we can write A equal to B. That is A and B are composed of same elements, same number of elements and same elements, then they are called equal sets. For example, set A, x is such that x square is equal to 1. Now x square is equal to 1, that means x equal to plus minus 1. So the values of x can be plus minus 1. So we can write set A is equal to minus 1 and plus 1. Similarly, mod of x is equal to 1. Mod of x will be is equal to 1 when x equal to plus minus 1. If I take mod, in this case for plus 1 it is 1, for minus 1 take mod, answer will be plus 1. So mod x is always positive, that's why x can be negative or positive. So the magnitude of x can be is equal to plus 1 or minus 1. So set A and set B composed of same elements and same number of elements, that's why A and B are equal sets. Now you have to remember this notation. The number of elements in a set A is denoted by n of A. N of A, or you can also write mod of A. This notations means the number of elements present in a set A. You can write by n of a or mod of a. Mod of a and n of a denotes same things. It denotes the number of elements present in a set A. For example, in this set the elements are -1 and 1. There is 2 elements. So, we can write mod of a is equal to 2 or n of a is equal to 2. So, n of a and mod of a denotes same number of elements in a set. Now, equivalent sets. Two sets capital A and capital B are called equivalent if n of A is equal to n of B. That is, two sets A and B, they may be equal, may not be equal. They are said to be equivalent if they are comprised of equal number of elements. That is n of A is equal to n of B. Now, remarks. Two equal sets are equivalent. I already said two equal sets are equivalent because they have same elements and same number of elements, but equivalent sets may not be equal. Yes, two sets may be equivalent because they have same number of elements, but it does not mean that they have same elements. That is why two equivalent sets may not be equal in many cases. Okay, this is your equality of sets and equivalent sets. Next definition is universal set. All the sets under discussion are the subsets of a certain set. In other words, in a mathematical discussion, the largest possible set is known as the universal set. Suppose if we are talking about the students of your classroom, then they are the subsets of the students of entire school. Similarly, if we are talking about real numbers, then this is the universal set for other numbers like integers, for natural numbers or whole numbers. That is why for number theory, the real number is the universal set of other numbers, and for your classroom the entire school is the universal set. So, universal set is the largest possible set in the mathematical discussion. Okay. So, if we say in universal set, it is the largest possible set in a mathematical discussion. Now, we denote a universal set by the letter capital U. Okay. Now, let capital A is any set, then A will be a subset of U, may be equal, not needed to know the number of elements. A and U can be equal, but A is a subset of capital U. For example, this is your real number, this is your Venn diagram. This circle denotes the set of all real numbers. Now, this is set of all integers Z. This is set of all whole number. What is whole number? Whole number starts from 0, 1, 2, 3, etc. And this is your natural number n. Now, this is your real number, this is set of integers, whole number, this is natural number. Now, Z is a subset of R, W is a subset of R, and N is a subset of R. Therefore, R is the universal set for these numbers. Okay. So, we can define universal set is the largest possible set in a mathematical discussion. Next is sixth definition is power set. What is power set? A set formed by taking all the subsets of a set is called the power set of a set A, and it is denoted by P of A. P of A denotes the power set of A. Now, a set is composed of two elements. Now, the total number of subsets you can generate from this set is 4. How it is 4? For example, if I take a set A comma B. Now, this set composed of two elements. Now, we already know phi means null set. Phi is a subset of any set. So if I start with phi, phi is a subset of this set A comma B. Now if I take the element A and we write in second bracket, it is a subset of this set. Similarly, if I take element B and write within second bracket is B. Now if I take both the elements A and B, A comma B, and write within the second bracket, it is also a subset of this set. I already said in remarks, A is subset of itself. So this subset has 4 different subsets. If I write them in second bracket, then it is the set of all possible subsets of the set A comma B. It means the power set of A. In other words, I can define the power set of A is the set of all subsets of a set A. That is, all the possible subsets of a set are written in a second bracket to make a set. It is called power set of this set. For example, capital A is equal to A comma B comma C. This set consists of 3 elements. Now if I take no elements from this set to form a subset, I will get a phi. Phi means set composed of no element. Now if I say take a set of A, only element A, I will get a set A. Similarly B, similarly C. If I take one element at a time, I will get 3 subsets. Now if I take 2 elements at a time, I will get 3 subsets AB, BC and CA. And lastly, if I take all the 3 elements of the set, 3 elements at the same time, I will get a set ABC. Now this P of A comprises of 8 elements, 1, 2, 3, 4, 5, 6, 7, 8. And for this there are 2 elements and its power set of A composed of 4 elements. Now I can generalize a formula, this is called result. If n of A is equal to m, that is number of elements present in set A is equal to m, then number of elements present in P of A, that is the total number of possible subsets of capital A will be is equal to 2 to the power m. This is 8, number of elements is 3, so it is 2 to the power 3, 8. This is 4, here the elements are 2, so it is 2 to the power 2, 4. So P of A denotes the set of all possible subsets that can be formed from the elements of a set capital A. So if you write n of P of A, it means the total number of subsets that can be formed with the elements of a set A. Okay. So if you know n of A is equal to m, then n of PA will be is equal to 2 to the power m. 2 to the power m. This formula can be verified using binomial theorem. Now operation of sets. Like algebraic operations, in sets there are few operations too. One is union. Now you have to be habituated with these symbols. This is union and this is intersection. In simple words, union means all and intersection means common. When I say union, we combine all the 2 sets, and when I say intersection, we take the common elements of 2 sets. Now union means the union of 2 sets capital A and capital B denoted by A union B. This is called union. A union B is the set of all elements which belong to either A or B or both. That is, the set A union B will be composed of those elements which are present in set A or in set B or both. Okay. For example, if I take set A is equal to 1, 2, 3, 4 and set B is equal to 3, 5, 6, 7. Now This element 3 is a common element of A and B. So if I write A union B, then I will take each and every element present in set A or set B or both. So I will start from 1, 2, 3, 4. The elements of set A, and I will list the elements of set B too. Now in set B, 3 is a common element of A and B. So 3 is already listed, so you will write only 5, 6, 7. Now this is your A union B. A union B denotes the set of all elements which belong to either A or B or both. This element 3 is present in set A and set B too. Now in symbol, A union B is equal to, in Serre-Bildner method, X is such that X belongs to set A or X belongs to set B. Now the element X of the set A union B will belong to either A or B. Clearly set A is a subset of A union B and set B is a subset of A union B, because all the elements of A are present in A union B and all the elements of B are also present in A union B. So you can say that A is a subset of A union B and B is also a subset of A union B. If A union B is equal to phi, that is the union of two sets is equal to phi, is a null set. Now A and B are two different sets. Now their union is a phi. Phi means null set. That is a set composed of no element. Therefore, we can write A is equal to phi and B equal to phi. Because in A union B, we list all the elements present in set A or set B. Now, how can A union B is equal to phi if A and B are non-zero sets? So, A and B should be null sets. So, A equal to phi and B equal to phi. Now, if A is a subset of B, now A is a subset of B, that is each and every element of set A are also present in set B. Therefore, entire A is a part of B. So, you can write A union B is equal to B, because all the elements of A are also present in B. That is, the elements of A are common in B. So, entire B will be the A union B. This is the case. Set A and set B. If you find their union, your answer will be set B only, because entire A is present in set A. Operation of sets number 2, intersection. The intersection of two sets capital A and capital B, comma, denoted by A intersection B. Remember, this symbol represents intersection and this represents union, is denoted by A intersection B is the set of all elements which belong to both A and B, that is the common elements of capital A and capital B. In symbol, you can write A intersection B is equal to X is such that X belongs to A and X belongs to B, where X represents any element of set A intersection B. In Serre-Bildner method, it represents the set of all X which belongs to A and which belongs to B. And means intersection, and OR means union. When I say AND, it means intersection, and when you will say OR, it means union. If A intersection B is equal to phi, then A and B are disjoint sets. Two sets A and B are said to be disjoint sets if they have nothing in common. Also, A intersection B is subset of A. What is A intersection B? The set of all common elements of capital A and capital B. That's why A intersection B will be subset of capital A, capital B and A union B. So, we can say that A intersection B is subset of capital A, capital B and A union B. If A is a subset of B, that is all the elements of capital A are also present in capital B, then A intersection B is equal to A, that is entire A is common between A and B. Hence, if I find the intersection, it will be is equal to capital A. This is your intersection. Now, number 3, operation of sets. 3. Difference of two sets. The difference of sets capital A and capital B, comma, denoted by A minus B, is the set of all elements of A which are not element of B. That is, the elements which are present in set A only but not in B. For example, if you take capital A is equal to 1, 2, 3, 4 and capital B is equal to 3, 4, 5, 6. Now, if I find A minus B, then in the set A there are two elements which are present in set A only. Therefore, A minus B will be 1, 2. That is, A minus B is the set of all elements of capital A which are not element of capital B. That is, the elements which are only present in set A, not in B. In symbol, or you can say in set-builder form, we can write A minus B as X is such that X belongs to A and X not belongs to A. Here X belongs to A and X not belongs to B. Similarly, B minus A will be X is such that X belongs to B and X not belongs to A. Now, A minus B is subset of capital A. Obviously, A minus B denotes the set of all elements which are present in set A but not in B. Therefore, A minus B is subset of capital A and B minus A is the set of all elements which are present in B not in A. Therefore, B minus A is subset of capital B. These are some terms you need to remember. The set A minus B union B minus A. If I find the union of A minus B and B minus A is called the symmetric difference of capital A and capital B, and it is denoted by A del B, where this symbol means del, capital del. So, A del means A minus B union B minus A is called the symmetric difference of A and B. If A is a subset of B, set A is subset of set B, then A minus B is equal to 5 because all the elements of A are part of B. So, there is no such element present in A which does not present in set B. Therefore, it will be A minus B is equal to 5. For A minus B, if A minus B are disjoint sets, that is, if between A and B nothing is common, so entire A is present in A only. So, A minus B will be is equal to A. Similarly, B minus A will be is equal to B. This is your difference of sets. Number 4, complement of a set. Let capital U be the universal set and A is subset of U. Then the set of all these elements in the universal set U which are not the elements of set A is called the complement of A. That is, the elements which are present in set U but not present in set A is called the complement of A, and it is denoted by A dash or A complement. C means complement. In symbol, A complement is equal to set of all elements X such that X belongs to U and X not belongs to A. That is, the set of all elements which are present in U only but not in A. We can also write AC is equal to U minus A, that is difference of U and A. It means the set of all elements present in U but not in A. This is called U difference A. Okay, this is your A complement. These are the 4 operations of on sets. One is union, other is intersection, then difference, and then complement of 2 sets or of a set. These are the 4 operations you need to learn. Now there are some laws of sets. Laws of algebra sets. Number A, complement laws. I have listed A, B, C, D, E, F, G. There are 7 different laws of algebra of sets. So you have to write these laws in the copy so that you can use in upcoming numericals. What is complement laws? If I take complement of universal set, I will get phi, because what is universal set? It is the largest set in mathematical discussion. So if I take its complement, you will get nothing, no elements are left, so it is phi. And if you take the complement of phi, you will get the universal set. This is a theoretical concept. Okay, the theoretical concept, you have to memorize these things. If you take complement of a set and then you take again complement, you will get the set A back for any set A. If you find the union of A and A complement, that is, if you add A and A complement, you will get the universal set. What is A complement? Denotes the set of all elements present in U which are not present in set A. So if you find the union of A and A complement, you will get U. And number 4, A intersection A complement is equal to phi. A and A prime or A complement are disjoint sets. There is no common element between A and A complement. This is your complement laws. Number B, idempotent law. Idempotent law. For any set capital A, this property is possible only between same set. For any set capital A, if you find A union A, your answer will be A, because entire A is common to A only. So if you find the union, you will get A by A. Number 2, if I find the intersection of A and A, you will get A only. This is number C, identity law. It denotes A union phi. If I find the union of a set A with a null set, you will get capital A. And number 2, if you find A intersection U, you will get A. If you find the intersection of A and universal set, the largest possible set of mathematical discussion, the common will be capital A. Number D is commutative laws. For any two sets capital A and capital B, if I find the union of A and B and union of B and A, it will be equal. Similarly, if I find the intersection A and B and B and A, it will be always equal. Number E is associative laws. For any three sets capital A, capital B and capital C, number 1, A union then B union C is equal to A union B then union C. Number 2 is A intersection B intersection C is equal to A intersection B intersection C. Number F is distributive laws. Distributive laws. It means if you are given A union B intersection C, then you can distribute the intersection. So it will be A union B intersection A union C. And number 2 is A intersection B union C is equal to A intersection B union A intersection C. And number G is De Morgan's law. This is very important for board level problems. De Morgan's law. It denotes number 1 is A union B. If I find the union of two sets A and B and then you find its complement, the result will be A complement intersection B complement. It is equivalent to the intersection of the two complements of A and B. And number 2 is A intersection B and its complement is equal to A complement union B complement. Similarly, if I find the intersection of two sets A and B and then I find its complement, it will be equal to A complement union B complement. These are 7 different laws of algebra of sets. You have to memorize these laws to solve the upcoming problems of set theory. Now it's time to discuss Venn diagram. What is Venn diagram? VENN Venn diagram. Venn diagram is the system of representing sets in diagrammatic way. In Venn diagram, we denote the universal set by a rectangle and the subsets as circular figures. Like we denote this rectangle as universal set and these elements, these circular figures as subsets of U. Let A and B be two subsets of U, where U denotes the universal set. So, if I find their intersection, then I will write if these sets capital A and capital B has something in common, that is they possess some common elements, then this area represents the common elements of set A and set B. This is capital A, this is capital B. This part denotes A intersection B. This is Venn diagram of representing A intersection B. Now, if you say this is your universal set capital A and capital B, and if you are to denote A union B, so what does A union B means? The set of all elements that belongs to A or B or both. Now, these elements are present in set A only. So, you have to include this. And these elements are present in set B only. You have to include this, and these elements are present in set A and B both. So, I have to include all the possible areas of A and B. This is your A union B. In Venn diagram, this area represents the elements of A union B. Now, what is A difference B? Okay, if I rub this, this is your A minus B. This is capital A, capital B. This is universal set. Now, what is A minus B represents? The set of all elements which are present in A only but not in B. Now, this area represents the elements which are present in set A but not in B, because this region is the common of A and B. So, I have to subtract this portion from A. This represents A minus B, and this region is common to B only. So, this represents B minus A. In Venn diagram, we can represent the system of sets in a simpler way, and it is very useful in solving numericals with number of elements present in any kind of sets. Okay, so we'll use Venn diagrams when you will solve different problems, including finding number of elements present in a particular set. Okay, so Venn diagram is very important, and I will keep on drawing different cases in upcoming problems using Venn diagrams. What is Venn diagram? In Venn diagram, we denote the universal set by a rectangle and the subsets by a circular figures. This is all about Venn diagrams, and we will keep on drawing different cases in Venn diagram in upcoming problems or theories. Theorem of number of elements of set. If capital A and capital B are two finite sets, then n of A union B is equal to n of A plus n of B minus n of A intersection B. That is, the number of elements present in set A union B is equal to n of A, number of elements present in set A, plus n of B, number of elements present in set B, minus the number of elements present in set A intersection B. So, how to find its solution? By proof. remember, if capital A and capital B are two disjoint sets, that is, set A and set B has nothing in common, that is, A intersection B is equal to phi. Set A and set B has nothing in common. So, if you find the number of elements of A union B is equal to n of A plus n of B. For example, if you take capital A is equal to 1, 2, 3, 4 and capital B is equal to 5, 6, 7. Now, set A and set B has nothing in common. So, if you find their union, your result will be 1, 2, 3, 4, 5, 6, 7. So, if you find the number of elements of A union B is equal to 7. What is 7? 7 equal to 4 plus 3, that is n of A plus n of B. When two sets A and B has nothing in common, when you find their union, the total number of elements will be is equal to sum of the individual number of elements present in the both sets. So, now let two sets capital A and capital B intersect, that is, they have something in common. This is your universal set, set A and set B. Now this portion is your A intersection B, that is the common elements of A and B. This portion is your A minus B, as I already mentioned in Venn diagram. And this area portion is your B minus A, that is the set of elements which are present in set B only. Now this is your A union B, this entire region. So we can divide A union B into three disjoint sets, A minus B, comma A intersection B and B minus A. B minus A. So, if I find n of A union B, which will be is equal to the sum of the individual number of elements of the three disjoint sets. So, n of A union B is equal to n of A minus B plus n of A intersection B plus n of B minus A. Now, what is A minus B? The elements which are present in set A only. So, n of A minus B. If I write n of A minus B plus n of A intersection B plus n of B minus A plus n of A intersection B. Now, I have written n of A intersection B twice, but it is only once. So, I must subtract once n of A intersection B. So, this is n of A minus B plus n of A intersection B. So, this is, so if I remove this part, I can write it here. This is n of A minus B plus n of A intersection B. This is what? N of A minus B, this part plus this part, that is n of A. This is n of B minus A, n of B minus A plus n of A intersection B. This is equal to n of B minus n of A intersection B. This is your proof of n of A union B.